Hello, everyone. It's my great pleasure to welcome our guest today, Professor Enrique Gaztanaga. Professor Enrique Gaztanaga is based at the Institute of Cosmology and Gravitation at the University of Portsmouth. And his area of expertise is in cosmological models and large scale structures. I try to look into his bio and profile, and I'm so deeply impressed. I'm not sure if you know, sir, but you have over 1,000 articles in Google Scholar. This is absolutely incredible. You have actually more precisely 1,151. You achieved 72,467 citations. And this is a number so stratospheric that there are Nobel Prize winners with a fraction of this number in terms of citations or H index. Your H index is 126. So this is incredible results. I'm so impressed by your academic caliber. For your achievements, so for his achievements, Professor Gaztanaga received many awards. The latest in 2024 was the Freedom of the City of London. This is an award that dates back to 1275, and he was awarded by the Lord Mayor of London. So very impressive to be included in the list of awardees for this. Today, the focus of this short interview is a recent paper that Enrique, I hope you don't mind I call you Enrique, and I'll drop the professor. It's a recent paper that Enrique published more precisely in May 2025. And the paper was published in PhysRevD, gravitational bounce from the quantum exclusion principle. And the article it attracted a lot of media interest, and it was backed by another article published in The Conversation on the similar topic. This is a technique I deploy myself. I tend to publish an article and then back it with another article in The Conversation to increase the uptake and citations and maybe get some media interest. It's not always possible to do this, I'm afraid, but when I can, I do back to back an article in The Conversation. And so this, as I said, it has been a lot of buzz around this article, and is truly interesting. So I'm just going to go to a few questions. In your paper, Enrique, you argue that the Big Bang could be a bounce in a nutshell. The article is complex science. Is not very simple to digest. But in a nutshell, you argue that the Big Bang could be a bounce inside a black hole rather than the traditional view of a Big Bang with a true beginning. And this challenges the consensus that the universe began with a Big Bang. So in plain terms, can you explain to our viewers this research and this science? What is behind this, and how do you explain your findings?
Yes, well, thank you first of all for the introduction. The idea is behind this model there is a single idea, which is more like a principle that applies to all physics, and is the principle that infinites don't exist in physics. So infinite is a very important and interesting concept that emerges in mathematics. We use infinites all the time as a tool to do accurate mathematics. But sometimes physicists forget that infinites are not within the laws of physics. Infinites cannot exist because they cannot be verified. In any empirical law requires a verification, and it will take infinite time to verify an infinite, and therefore infinites are not within the scope of empirical laws. But because we have a strong formation in mathematics, many physicists and scientists forget that infinites are mathematical concepts. So anytime you hit an infinite, it's a warning that you are extrapolating outside the empirical laws of physics. And in the case of the universe, it appears in two different forms. First of all, the current Big Bang picture that most cosmologists have is based on an infinite space-time. So the mathematical modeling requires that the space-time is infinite, and not only that, but is filled with uniform matter content, energy and matter content, that is the same everywhere in the whole infinite. And of course, this doesn't make any sense. It's not only not an empirical possibility, but it's also not causally possible. You cannot have the same energy and density in everywhere, because it will take infinite time to produce that, and there is no mechanism in physics that can do that. The propagation speed of any phenomena in physics is finite. This is very important. This was realized soon after Newton thought about instant propagation to understand gravity, and this has very strong implications. Of course, the most important one is relativity. Relativity emerged as a manifestation that the propagation speed is finite, is not infinite. And it also manifests in quantum mechanics. Quantum mechanics tell us that you cannot divide energy, or in particular, more specifically, the action. You cannot divide the action in infinite pieces. There is a finite amount you can do, which is what we call quantum.
That's right. We have not only the upper limit with the speed of light, but also the Planck lengths and the Planck limits. So it appears that the universe screams at us finite from all edges, if you want, from all intervals, limits, but we still deploy models that assume infinite space and an infinite universe. So I'm with you on this one 100%. Sorry to interrupt you.
Yeah, it's an approximation, right? So what we do in physics is we do very simplistic approximations, which is nice. I mean, it's good. It's the first step. We approximate the universe as infinite, fine. The consequence of that is that, well, if you use the standard laws of gravity, and you have and you use this infinite universe, then you also get this infinite beginning, which is what we call the Big Bang. Mathematically, we call it a singularity, because if you go back in time, we are currently observing that the universe is expanding. But of course, if you go back in time in this expansion, the laws of physics, when you assume an infinite universe, gives you an infinite density at the beginning, which is, again, a contradiction. It's just telling us that those approximations don't hold together.
Yeah.
So the base of the model is, okay, let's reduce the level of simplicity one step. And why we do that is because the current laws of cosmology are extremely successful in predicting observations in many aspects with just a few parameters. But the fundamentals of these models are not well understood. They are based on this infinite singularity at the beginning. Then we also have this dark matter that we don't understand. We have this dark energy we don't understand. We need a period of inflation to understand structure formation. And there are also some other mysteries that are now coming up with recent data from the James Webb Telescope, and it has been piling up for years about the nature of galaxy evolution and the relation between galaxy evolution and supermassive black holes. And again, the appearance of black holes now in the universe, which is something relatively recent, also opens these questions, because when you try to understand black holes and combine them with the laws of quantum mechanics, you end up into paradoxes that are again related to these infinites.
Yeah.
So anyway, this is like the context of
So
the model.
should I understand that this was not an accidental discovery? You were actually targeting solving some of these critical problems, such as the singularity with the Big Bang and the inflation model that it doesn't hold water 100%. So it wasn't a case where in many instances in research, someone does a piece of research, maybe solves um, a, a typical set of equations, and the solutions point to something unexpected, and then the interpretations follow. You actually targeted exactly solving some of these problems in terms of the cosmological models. Am I wrong to assume that? Because my understanding is that you eliminate basically this problem of singularity is eliminated with this new proposal that you discovered, and you also don't need inflation. It comes naturally from this. So was it intentional then?
Yeah, I mean, curiously, the threat to this model started some time ago when I was trying to explain to students and to myself, because that's when we learn physics, is when we give classes, right? Where we explain to students. And I was trying to explain the cosmologists call it the cosmological principle. The cosmological principle is a principle or an assumption by which the universe is infinite, and it has the same energy density and density of matter everywhere. And of course, this doesn't make any sense. So I was then trying to understand another problem that we've been working in the last 30 years. And a lot of these papers that you mentioned come from that effort where we built teams to do cosmic surveys to understand cosmic evolution. And cosmic evolution tells us that the universe is expanding in an accelerated way. And this doesn't make any sense. So then, because it doesn't make any sense, we invent this concept of dark energy, which is a way to try to understand how the universe could be accelerated. And then suddenly I was wondering whether the origin of this acceleration could be related to this assumption that the universe is infinite. And indeed, I find this connection that you can, in fact, remove the infinite approximation from the models, still have the same models, which is, the same principles, uniform anisotropic universe, but not infinite. Now, how is
So
that possible?
sorry for interrupting, but am I wrong to understand that by doing so, you eliminate the need for dark energy as well?
Exactly.
Because
How it
if I remember correctly, initially the Einstein's model assumed a finite universe and also a static universe. This is why he introduced the cosmological constant to to force the universe into this static equilibrium state, and then he called it the greatest blunder, if I remember correctly, and it turns out it's been repurposed to explain the expansion of the universe and the accelerated expansion. But you are saying that there might not be any need for that if you assume a finite.
Exactly.
Late. That's amazing.
So that's the first thing we realize, is that when you put this lambda cosmological constant lambda term that Einstein, as you well said, introduced in 1917, long time ago, just right after he proposed the new theory of gravity, which is general relativity. He applied that to the cosmos and he introduced this cosmological constant. And now, when we observe cosmic expansion, what we see this cosmological constant, and it's not a small effect, it's a huge effect. You know, about 70 to 80%, closer to 75% of the energy in the expansion is due to this cosmological constant. And in the future, it will be even bigger. And so it looks like our universe likes this cosmological constant. And you can very easily realize that this cosmological constant is related to the finite mass of the universe. So if you start with a model that is not infinite, that is finite, you can very easily work out that the mass of this finite universe is related to the cosmological constant. In fact, the cosmological constant is the inverse of the square root of the mass of the universe.
Okay, so you don't eliminate the cosmological constant; you keep it in the model, in equations and the model. You don't actually. It's a necessity.
No, you don't keep it. It's just the mass of a finite universe.
Right.
We call it the cosmological constant, but we should call it the mass
Okay.
of the universe. So the bigger the mass of the universe, the smaller is the cosmological constant. If the universe was really infinite, there will be no cosmological constant. Because the universe is finite, then there is a cosmological constant. It's an effective cosmological constant, but it's a constant. It's exactly the same thing. Yeah. And so, then immediately you say, oh, wow. So if the universe is finite and there is a mass, that explains the cosmological constant. Fine. We are explaining one of the founding issues with the Big Bang model. But why are we expanding? The natural thing for a finite cloud. So imagine, the analogy is a star. How stars form? What happens is that there is a cloud of matter, usually is hydrogen, but it doesn't really matter what it is. Whatever it is, gravity put this cloud, attract these clouds together and makes the cloud higher and higher density and smaller and smaller scale. So this is called gravitational collapse. We see that all the time. That's what happens in our universe. There are very small instabilities in gravity that create these inhomogeneities, and these give rise to stars and galaxies, right? So could the universe have started the same way, right? Because if it is finite, it is a finite cloud, then the natural thing for it to start is not out of a infinite Big Bang, but out of collapse, right? So that's the starting point. Once you realize that the cosmological constant is the mass of the universe. And the other thing you realize that is very important to note is that the same way we are trapped here on Earth, we are trapped going around circles around the sun. Why is that? It's because matter, gravity, the mass of the sun, creates curvature. And then we are trapped in the curvature of the sun, okay? This is a very important concept. If the universe have mass, it will have a cosmological constant, but it will also have a curvature, an intrinsic curvature that should be there.
So this is this the reason that you introduced a small positive curvature in your assumptions in the original paper? You have a small k positive there, and is that the motivation? Is this why you introduced that? Because that was my next question.
What motivation
was my next question? I see the logic now. I see the logic.
Any perturbation, so
I see the logic.
Any overdensity, because you are above the mean density, any overdensity will have curvature. That's exactly what happens.
It makes sense.
That's exactly what happens on Earth. Curvature is part of gravity. You cannot have gravity without curvature. Gravity gives you curvature. So the minute the only way you can have gravity without curvature will be in this infinite extrapolation. in this infinite extrapolation, you have the choice to have zero curvature. So basically, you can think of curvature like the size. So, you have the mass and you have the size. So curvature is related to the size. So if the universe has a finite mass, it also started with a finite size, and that size is the curvature. And so what happened is that now imagine a cloud that is collapsing. As you collapse, the size reduces, and the curvature is inversely proportional to the size squared. So basically, the smaller the cloud as it collapses, the larger the curvature. And so this is very important because this is what is going to prevent the universe from going into a singularity when it collapses. So there are two ingredients. One is the curvature, and then the second ingredient, which is the origin of this paper, is to realize that you cannot actually collapse a star or anything into zero radius, right? Because of the exclusion principle in quantum mechanics. Quantum mechanics tell us that infinites don't exist. You cannot put a finite amount of matter into zero space, right? You cannot put two things together in the same location. There is a minimum quantum, which is given by the Planck constant, right? And this is called the Pauli exclusion principle. That's how we understand white dwarfs and neutron stars. It's called degenerative pressure, right? So when you compress matter, we can see every day that when you compress matter, matter resists compression, and this creates an explosion. It's called a supernova explosion or core collapse supernova. And that's exactly what I think happened with our universe. It's a finite universe with finite mass and finite curvature, collapses, and when it reaches nuclear saturation, when it reaches this quantum state, and you cannot overlay one particle on top of each other, they exclude each other,
Then it bounces.
then it bounces. And this you can show mathematically, this bounce.
Yeah.
It's very beautiful. If you just go to a ground state, general relativity, classic equations of general relativity, shows the equation of the bounce, which is the parabolic cosine.
It's a very nice article. In the video, I have links to your articles, the PhysRevD and the conversation article. For whoever watches the video, if anybody wants to go deeper, I have links to Enrique's articles. Amazing work. So now it makes sense. Now I was wondering why why you needed a positive curvature. Now it makes sense now. Correct me if I'm wrong, but you are saying that for an observer that is outside, in this model, there is an outside. So the entire universe would be inside of a black hole. And for an observer outside, you will see a black hole. For an observer inside, which is us, we see a universe expanding. But we are inside of a black hole. Is that the correct picture that I took from the research? So assuming this is correct, then are you supporting the multiverse theory maybe? Because I'm imagining a scenario where there would be other black holes where the same process took place, and there will be other universes existing inside those black holes. And so yeah, this is quite fascinating stuff. I mean, what's your view on that?
Yeah, I mean, of course, it becomes a bit of a speculation once it's really a bit outside the realm of what we can test right now. Although, there are some ways we can test some of these ideas. But you are right. I mean, once you understand the process, then you say, well, if our universe is a cloud that collapsed in a larger background, there could be other clouds like ours, or bigger or smaller, that also collapse. And we know that there are black holes within black holes, meaning that within our universe, which is a black hole, there are other black holes. And therefore, there could also be other black holes within those black holes, right? There's nothing wrong with that. That's totally Correct. Now the question is, what can we really infer from the outside, if there is really an outside to our black hole universe? If there are other black holes, will we ever know anything about them? Is there a way to get information from outside? And in fact, there is. It's pretty amazing. It turns out that there is a process in which, when our universe was collapsing, it very likely also formed galaxies, planets, stars, and other black holes as it collapsed, right? Those structures that were created before the Big Bang, pre-Big Bang, during the collapse, can actually survive the bounce. And this is really cool. This is something that is mathematically very easy to show, that relics from the past can survive the bounce. Moreover, in the bounce itself, you create also more relics, you create more black holes. All of these are archaeological relics that we can actually observe today. And we think that dark matter, what we call dark matter, could actually be made of black hole relics from the bounce. And this is something that, well, right now is a speculation, of course. We don't know what dark matter is. After 50 years searching for it, we haven't found what it is. But dark matter could well be black holes. And so this is something that very soon we are going to be testing. We already have some clues in these directions. For example, every galaxy has a supermassive black hole. And now with the James Webb Telescope, we are seeing these little red dots, which are active galactic nuclei, which is supermassive black holes in the early universe, that almost have no stars. So we are starting seeing this primordial, which I call more relic, more than primordial black holes, that could be the result of coming from the previous epoch of the universe. And by measuring that, we can actually get an idea of what was the conditions of the collapse that happened before. And from those conditions, we might learn something about what is the background in which our universe collapsed. So it's very difficult, it's indirect, but there is a connection that will soon tell us whether this idea is right or wrong. If we don't find any curvature to a high precision, we don't find any relics, then it's not necessarily mean this idea is wrong, but the empirical support for this idea will be more reduced, and it will become more like a possibility rather than a reality. But on the other hand, it could well be that in the next few years, very soon, we will have more evidence in this direction of relics from the previous Big Bang.
So this is very, very exciting that there are testable avenues to actually verify this theory. It's not pure theoretical and left in the speculative realm. That there are ways of actually looking at this empirically. So this is very, very encouraging. From my angle, if you are marginally familiar with some of the research I'm doing, I'm interested in the field of information physics, and some of the research that I do points to this idea of a computational universe. And I'm not going into details now, but in everything I do, I kind of I'm on that side of science where the universe must be finite, um, where there is an outside, there is another, as it would be a base reality if you want. There is an outside, and I found the synergies between the stuff you are talking about, although it's a different, you take it from a different angle, completely different angle, but the fact that you support and the scientific findings is not just a belief, it's backed by calculations and solid foundations. You support the idea of a finite universe, and the fact that your science shows that we could be inside a black hole and there could be an outside. There could be something which we can't tell what is that beyond that, and it raises more questions than answers, to be honest. It's like anything else. The more we discover, the more we innovate, the more questions we get. It's quite frustrating. But to me, it felt it's a different angle, looking at almost the same thing, but from a different angle. This is fascinating stuff, and to wrap it up, so you kind of answered my question, but I was aiming to ask what's your next plan, and especially around the empirical evidence of this. So would for example a non-zero spatial curvature of CMB, would that be a if it's detected, would that be a supporting evidence of your theory?
Everyone would be very strong support evidence.
So what else are you targeting about besides this? What's next in terms of like this research?
I think one of the most difficult problems now in cosmology is called galaxy evolution. How galaxies are formed. This we still don't know. We do have simulations and very elaborate theories. We think it's a complex process, but maybe we got the initial conditions wrong. So as I was saying, if dark matter is made of black holes, this will probably change a lot the way we understand galaxy evolution. And nowadays, with new cosmic surveys, in particular the Beta Rubin or LSST survey, the Euclid survey, and the new space telescopes like the James Webb Space Telescope, we are opening a new era on understanding galaxy evolution. And my impression is that it is there where we're going to find surprises. And as I said, these relics, if we find evidence that there were big black holes before, even before the cosmic microwave background, that is something that can be related to anisotropies that we see in the microwave background in the spectrum. So there are ways in which we can connect these models with observations, and this is exactly what I'm working on now. In particular, just this week, a new paper in Physics Review Letters is appearing about these bounds dark matter as relics, and there is a lot of work needed to make those predictions. I also want to mention that yes, I read your papers on the computational universe, and in fact, I was in one of your talks in Portsmouth, and I think this is a very interesting idea that needs to be explored. There might be some connections there between, as you know, black holes have this analogy with
Information paradox.
entropy.
Yeah.
Exactly. An information paradox. So there are connections there that need to be understood about this idea of whether there is more to it and whether we can learn more about the pre-Big Bang, what happened before. And basically, what we need is just people working on this. And this is what I'm trying to do. I'm trying to put some effort in moving in this direction. And I just hope more scientists join us looking in that direction.
So yeah, I think I remember seeing you. Was it the lecture on second law of information dynamics? I think I remember seeing you in the lecture theater. Oh yeah, thanks for attending that. So to wrap it up, my understanding is that the latest observations from James Webb and everything else, all the satellites and the new tools you guys have in astrophysics and cosmology, they turned a bit upside down the existing models. So I think you coming up with these new ideas and anything that is different, is not inflation, is not Big Bang cosmology, is not anything different, I think it should be welcomed with free hands, because we need to start looking beyond the current consensus and see what new ideas are out there and test them, put them to scrutiny and investigate as much as we can. So I think it's quite commendable what you are doing. Enrique,
Yeah, what we should do as scientist, right, is to
It-
to push the frontiers
I'll
of knowledge.
next time I'm on campus, I'll buy you a beer. That's on me. I'm so grateful for this interview, Enrique. This is an honor to have an academic of your caliber talking to us. And I can't wait to read your Phys Rev Letters article. When that is out, let us know, and we are going to review this, and surely we're going to have you back live. Thank you, sir, and all the best.